Hey, this is Mr. Aiden. This is AP Chemistry. We're going to be going through the 2018 AP exam. We're going to be going through problems number 4 and 5. Now, problems number 4 and 5 are both 4-point problems, so let's get to it. The first one is an intermolecular forces problem. You can see we have CS2 right here. We have sulfur atoms on the outside. We have the carbon atom in the middle. That looks so much like carbon dioxide, doesn't it? And so because it is a linear shape, you know right away that that is going to be nonpolar because it will be there's symmetry throughout. There's no asymmetry. And so that linear shape is going to be a nonpolar molecule. Now you take a look at this COS, and obviously you can see the oxygen atom is going to hold the slightly negative charge, which means it will be a polar molecule. Polar molecule, since there's no hydrogen in there, there's not going to be any, even though it's still linear, there's an asymmetry there. And so there's going to be a positive side of the molecule, negative side of the molecule, so you know it is polar. So right away, you know some things. A says, in terms of the types and relative strengths of the intermolecular forces, explain why the boiling point of CS2 is higher. Well, we know CS2 is linear, it's nonpolar. Therefore, it only has London dispersion forces. Okay, while the COS molecule is polar, which means it's got dipole to dipole forces as well as London dispersion forces. Now, why in the world would London dispersion forces beat out the dipole to dipole is the CS2 has more London dispersion forces, because it is more polarizable. It has a greater polarizability, more polarizable, and therefore it will have stronger intermolecular forces and therefore have a higher boiling point. Okay, this was a 2-point part of the problem. You can see 1 point is correctly identifying the intermolecular forces in both substances, and then 1 point for the specification of there's more London dispersion forces, there's stronger London dispersion forces, there's more polarizability, and therefore higher boiling point. So that was worth 2 points for A. Now once we get to B, B you can see is going to give you 10 grams of CS2. Well, what do we do anytime we know 10 grams of a substance is divide by his molar mass? So divided by 76.13 grams per mole gives me 0.131 moles of CS2. Now I can go anywhere. You can see it is a vaporized, a gas problem, so I'm going to use PV equals nRT. We're trying to find the pressure. I know the volume of the container is a 5.0 liter container. The number of moles, I just found it, 0.131 moles. I know the R. I'm going to use the 0.08206 because it's liters, atmospheres over moles, Kelvin. I need my temperature to be in Kelvin. It already is, 325 Kelvin. And therefore the pressure ends up becoming 0.70 atmospheres there. I round the 2 significant digits because you can see the 5.0 is 2 significant digits. That's the lowest amount. That B was worth 2 points. 1 point for finding the correct number of moles, 1 point for then applying it to Pivnert and getting your pressure. So 4-point problem. You can see 2 points for A, 2 points for B. You'll be able to score yourself. Let's go on to problem number 5. Problem number 5 is a equilibrium acid-base problem, and you can see they have something with the percent ionization. I know there's 13% ionized. It's therefore a weak acid. We only have 0.035 molar of the HF. It's a weak acid, and you can see which one looks like a weak acid. What do we know about weak acids? They do not dissociate 100%, which means figure 1 is going to show my weak acid. They asked us, they said 2 representations, explain why the representation of ionization in HF in water for figure 1 is more accurate. Well, HF is a weak acid. What do I know about that weak acid? It is only partially ionized. It is not completely ionized. It is only 13.0% ionized, which means there will be very little amount of the H3O plus or the H plus. And so that was worth 1 point right there. 1 point for that discussion, that answer. So 1 point for A. 1 point for A. Let's go to B. B then says, use the percent ionization to calculate the Ka for HF. So what do we know here? Well, we know if it's 13.0% ionized, that is the amount of H plus, that's your X, over your initial molarity of 0.0350 molar, of course, times 100%. So that's 0.13. Therefore, you can find X or the H3O plus, or you might call it the H plus, and that ends up giving me 0.00455 molar. Okay, and that is my X. Now, this is a primary topics equilibrium problem, which means what do we know about Ka? That Ka breaks up into F minus times your H3O plus or your H plus over your HF. And so we know it's a very, very small percent ionized. What do we do with our X? We plug him in the numerator. We have X times X, and we have the HF initial concentration minus the X, don't we? And so you have 0.00455 molar, 0.00455 molar, and we plug in 0.0350 molar minus 0.00455 molar, and that gives me a Ka of approximately 6.81 times 10 to the negative fourth. And so you can see this is going to be worth 3 points. 1 point for calculating your H plus. Only worth 2 points. My bad. Only worth 2 points. 1 point for applying that then and calculating your Ka value. Primary topics equilibrium problem right there. Let's go to C. C is asking, we know if 50 mils of distilled water is added to these 50 mils, what's going to happen to the percent ionization? What do we always know happens when we dilute? I'll put this in a different color, sorry. What happens when we dilute a weak acid like HF with H2O? The percent ionization will increase. It will shift it towards the products. It will shift the reaction towards the products. Because of that dilution. And the F minus concentration and the H3O plus concentration will increase, which means it will increase in its percent ionization. Remember the KSP problems, we add water, nothing happens to that molar solubility. But Ka problems, Kb problems, we add water to it. The doubling the volume decreases the initial concentration by 1/2, and therefore it will shift it towards the products and increase the amount of percent ionization. That is worth 1 point for correct explanation, or you can also do a calculation with that. So you can see A was worth 1 point for calling it a weak acid, that it does not dissociate. B was worth 2 points, one for finding the H plus, one for then applying that and finding the Ka. And then C was worth 1 point. That's a 4-point problem. So score yourself. Give me your score. Hope you're doing good. Take it easy. See you guys. Bye.